Okay, here we go. So this test, like I said, is on rotation, which is almost only Chapter 8, but there is a little bit of Chapter 9, but that's just the balanced torques part. That's the only thing we're doing from Chapter 9. So we start off with, there's two different types of speed. There is linear speed and there is rotational speed. And that was the first challenge to understanding this stuff. We know that this was pretty much distance divided by time, whereas this is now some sort of rotation or angle divided by time. We could call that delta theta if you want. This is going to be measured in meters a second or in miles per hour, whereas rotational stuff could be measured in rotations a second, or RPMs is kind of the common way to do it. Or we could make up a new way to do it, which is what radians is. And just a quick review of radians. Remember, that's when you say that you're going to make up a new definition for an angle and call that new definition the length of the outside arc that you travel, call it L for arc length, compared to the length of the radius. So that comparison, that angle is the comparison between those two. And we're saying 1 radian then is when you have one arc length that's the same as the radius. And that was our definition of the radian. So if you go all the way around the circle, it's going to be like 6.28 times to get around that. So that would be 2 pi r with formulas. Then comparing that arc length to the radius, we can see that the ratio, which is what radians are, of the once around the circle is 6.28, or 2 pi radians to go all the way around the circle one time. So one rotation is 2 pi radians. I guess that's the big idea from that. Now, you don't have to use radians for rotational stuff, but it makes a lot of the conversions quicker when you're doing it if you do. So remember, the difference between these two speeds comes into play like with a bike wheel example. If you have something on the outer rim, call it 0.1, and then you have something halfway in, call it 0.2. If I ask you the question, which one is moving faster, you could say the outside one, which is 0.1, or you could say that they're the same, depending on which kind of speed you're talking about. They're the same if we're talking about rotational speed, because they're making the same number of rotations a second. The number 1 is greater if you're talking about linear speed, because now you're saying it's doing a bigger circle in the same amount of time. Okay, so that was sort of the first part, and then we got into new variables. And for the new variables, there were a lot of analogies to the old stuff, so the linear things versus the rotational. Now remember, another name for rotational was angular. It means the same thing. But instead of using theta, or delta x I should say, we're using delta theta. Instead of using velocity, we're using omega, rotational velocity or speed. Instead of acceleration a, we're using angular or rotational acceleration, alpha. Those are our 3 main differences. And then that gives us new formulas. And those new formulas were summed up in the equation sheet that you'll get to use. I'll probably give you a new one. So this is your angular speed, is this over that, angular acceleration, and then your 4 kinematic equations applied to rotational or angular things. Looks like that. The only other thing that was in the first chunk of stuff what we did, which corresponded to the first quiz, was we also went through some stuff that was how does linear stuff compare to rotational stuff. And kind of by playing around with that big wooden disc as a class, we figured out that a point on the outside edge, that the velocity of that as it's rolling, its tangential velocity, is exactly the same as the velocity of the center of mass of the wheel. And if I want to connect the rotational quantities to the angular one or linear ones, that connection is the linear equals the radius times the angular stuff, as long as this is in radians per second. That's why the conversion's easier. We also had the sister equation for acceleration. If you want the linear or tangential acceleration times the angular one by the radius. And same thing for this, it had to be in radians per second every second. So that was the first quiz, that stuff right there. The next material that we did was we started with torque. And we said torque is a twisting force. And we used the Greek letter tau to represent that. And the formula was the force matters, but also the lever arm, which we represent with R, and the two need to be perpendicular. And it actually doesn't matter if you make the force perpendicular, which is kind of what we most commonly do, or if you decide to make the lever arm perpendicular. They just both need to be perpendicular. We then said whenever you have what's called rotational equilibrium, that means all of the torques have to balance each other out. So that's like the problem we did with the mystery mass today. It also turns out that in almost all rotational equilibrium problems, they're also in static equilibrium, which means that the sum of the forces in the x is 0, and also the sum of the forces in the y is 0. So the only problems I'm going to give you are going to be ones where everything is balanced, not just the rotational, but it'll all be balanced. The next piece that we had was, instead of saying acceleration for linear stuff is force over mass, we had this idea that angular acceleration is not the force, but the twisting force, or the torque, divided by not just the mass, but where the mass is located, which we called the moment of inertia. And remember, for the most basic shape, which was a point mass being swung around in a circle of radius r, the moment of inertia for that was mass times radius squared. And all of the moments of inertia that we saw on the equation sheet and that we used involve some version of mr squared. You can't see those all that great, but they all have mr squared in it, and then it's just some sort of fractions to change it based on how the mass is distributed. And some of these look more complicated, but really it's just that you have two different dimensions to worry about, and they're the same sort of thing. You'll have those on the equation sheet. You don't have to memorize them or anything. We then had one last piece, and that last piece was, well, really two. Kinetic energy rotational is a new way to store energy. Energy could be stored in the rotation of, like the marble we did with the roller coaster. Remember, that was kind of our analogy for dark energy, that energy was hidden in a place that we hadn't expected. And this is 1/2 the moment of inertia times the angular velocity squared, which is very similar to 1/2 mass times velocity squared for linear linear kinetic energy. The last thing then we said is what we've done most recently, that angular momentum is moment of inertia times rotational speed, much like linear momentum is mass times velocity. This is a vector, so the direction matters for both of those guys. And the big idea for momentum was the momentum in the beginning, the angular momentum, equals the angular momentum at the end. A little bit of fine print. As long as there's no outside torque that changes it, then it's conserved. And typically that led to problems where we did like moment of inertia times rotational velocity equals a new moment of inertia, like a gymnast doing a flip. They tuck up and lower their moment of inertia, so that raises their rotational speed to make up for it. And that is that.